Nikolai, your turn, please. It is indeed hot topic because yesterday it was his talk was his research was mentioned at some conference. It is indeed hot.
Okay. Hello everyone. I'm very glad to see all of you here. I would like to talk to give a sort of this is going to be more of an overview talk on about the proof assistant and the formalization project that I'm involved with right now. So I'm basically the creator of the proof assistant, and the formalization is a collaboration, joint work with Emily Rio and Jonathan Weinberger from Johns Hopkins University. So I'm gonna break up the talk into several parts. First, I would like to just talk in general about category theory and synthetic theory and proof assistance, just a little bit to give the context for why it might be interesting to work on this in general, and where RZK proof assistant is in the context of other proof assistants, just in general. And then I'm going to talk a little bit about the synthetic infinity categories, but I'm going to do that immediately in the syntax of the RZK language, so in the syntax that the proof assistant supports. I'm not going to give like an entire full tutorial on the language, but I'm going to try and cover the most important parts from my perspective, the most important basics. Then I'm going to mention a few features or themes that I try to follow when I develop and think about possible improvements to the proof assistant and where it might go. Then I will mention the formalization project briefly. I'm not going to go into the details unless there are questions, and then we can just open the actual formalizations and I can show you what's where. And in the end, I will just conclude with some future work. This is very much work in progress, both on the implementation of the proof assistant and on the formalizations, even though we have some interesting results, I think, already. So without further ado, let's get into the context. So I want to start by just saying, because I imagine that most of the people in the audience don't do category theory most of the time. So I would just try to somehow justify why category theory might be an interesting thing, even if you're not interested specifically in mathematics, just pure mathematics. And of course, the way that I would like to give my examples, I would do that. Again, I would just mention other people's work that I'm not very well familiar with, but which I think is very inspirational, and I think that all of you can find some interesting things in there to maybe expand your understanding or to spark your interest in category theory. So I'm going to talk about category theory, and in particular infinity category theory. So typically we talk about higher category theory, where higher just means that we don't just have objects and arrows or points and arrows. We have some sort of higher structure. We have arrows between arrows and so on and so forth. There can be slightly different structures depending on specific theory that you work with, but all of those are basically called higher category theory. And there's also homotopy theory, which is not called category theory, but which is very much related. And the homotopy type theory, which we'll mention in a bit, this is related to very closely related to groupoid theory, and groupoids are just a particular kind of categories. So whenever you see homotopy theory or category theory, or maybe this word higher attached to it, basically in the very generally speaking, we're talking about the same sort of collection of theories, or very closely related collection of theories. So category theory has many applications, like in chemistry, in physics, in software engineering, in natural language processing. There are some other interesting things. These are just some of the fairly recent, which I found interesting for some reason. I think that for chemistry and natural language processing, sorry, I forgot. There's a mathematician. I forgot her name. Yeah, I think she has this nickname Mathema. Sorry, I forgot her name, but she has an interesting blog, and she has some interesting. She writes in an understandable for me way about these things, and she links a lot of interesting stuff, which is then easier to understand after going through her. So specifically about chemistry, applications to chemistry and natural language processing, I think I've learned through her. Yeah, and of course I am, I guess, first and foremost a Haskell programmer, and that means that I'm most experienced with just writing programs and designing programs and systems. So to me personally, the applications that I find interesting are those, for example, described in Fong and Spivak's book, 7 Sketches of Compositionality, an invitation to apply category theory. And I particularly like one of the ideas in that book, which maybe will be also useful in some sense to you. Maybe you will appreciate category theories a little bit more through this view. And this is the view where we say that database schemas can be treated as categories. And the way that you do this is you say that every table or every entity that you have in your database is a point or an object in a category. And then the arrows, the basically relationships between these things can be different things, but these are sort of generalized foreign keys. That's the idea. And of course, on top of that, you might have certain equalities, like here you can see that department .sacker.worksin equals department, which means that basically if you, from department, you go through sacker, so the secretary of that department, and then where does the secretary work? Well, it should be the same department. This is just a simplified version of saying that if you compose these arrows in this way, you get an identity. And you can have other identities, other constraints in the database schema. And of course, this is a very simple example, but there's an actual product that is being used and commercialized even, which talks about categorical databases. And again, I am not at all an expert, but I think that the general idea of perceiving database schemas as categories and talking about migrations as adjoint functors is very interesting. And it's very interesting to see that there is an entire product built out of that. Right. Then another application that of category theory that is a little bit closer to me is is when you implement let's say domain-specific language, or not necessarily domain-specific. When you implement a language in a functional programming language, for example, like Haskell, there are certain concepts that are algebraic in nature, and a lot of them come from category theory in particular, that are used to construct these languages in a somewhat composable way, but also to assist with meta generation of some sort, or to automatically have the properties that you want for the kind of language that you want to work with. And of course, there are a few very commonly used concepts, like free monads, for example, are used to represent syntax trees with substitution implemented automatically. There's also these data types a la carte concept by Swistra, which allows you to also do this in a sort of modular way. There are some restrictions, but you can basically join languages together and get other languages. You can compose in different ways. Monads, of course, are commonly used to abstract over any sort of imperative or SQL-like interfaces. And
what do you mean by SQL-like interface?
So, I mean, one kind of monads that is commonly used is basically. I think the microphone should pick up Abdurrahman well, but just in case the question was how do monads relate to SQL-like interfaces, and basically, if we simplify a little, there is a state monad which corresponds to imperative programming with state, sort of, and then there's a let's say a list monad that corresponds that you can treat as corresponding to non-determinism. But also there is list comprehension syntax, which is actually very close to what SQL looks like. And there are things like, for example, in C# LINQ in C# is basically an overloadable syntax, which is very close to monads. So yeah.
May I give very short
yes.
comment? You can disagree. You don't need to discuss or abuse this opinion. From my first day in Innoполis University, I remember one observation by Manuel Mazzara. Everything what do we study is a graph. Well, what I do it looks very much same. Everything what we study is category.
Yeah. So in category theory, I believe the key idea is that we want things not just to look like graphs. That's not the point. The point is for things to be composable in a nice way, so that when you so that you can either describe or build complicated things out of small things using operations that work well, so meaning that they preserve some good properties or entail some good properties of the overall structure, but also that are comfortable enough to actually use. And again, I'm using some of these concepts in a daily life when I'm programming in Haskell, so I can appreciate definitely some influence, at least of category theory, for that. One interesting thing that I would like to also mention is GHC generics, which is basically an algebraic representation of a user-defined data type that allows you to do type-safe metaprogramming and derive different processing over user-defined types in a generic way. And this is particularly. Yes.
What is acronym GHT stands for?
GHT is Glasgow Haskell Compiler.
Okay, thank you.
Right. And generics here are not generics like in Java. This is algebraic this refers to generic algebraic representation of a user-defined data type. The details do not matter that much, but for if someone is familiar with GHT generics, one foreshadowing maybe a little bit some future work, it's a similar idea, but based on not just algebraic data types, but on something with a higher structure, is I think something that might be very useful in a programming language that is richer in the sense that it, in some sense, embeds or internalizes this categorical language. And then the idea is that Haskell is, of course, a nice programming language with a powerful type system, but it cannot do everything. In particular, Haskell currently does not really have a dependent type system. It has some approximations, a lot of language extensions that approximate that. But then the idea is that if you have a language with which starts off with a richer type system, then you can achieve more, in particular with this metaprogramming and basically generating correct by construction code or something else by leveraging these richer structure. Right. So, for example, in Haskell, I can definitely implement a language in such a way that substitution is given for free, mostly, but I can only do that for relatively simple situations where I do not have some extra constraints that have to be considered or something else. So there's a specific form of the data type that I have to work with that allow me to do that. And with the richer language, we can achieve more. And there are some interesting motivating examples in Licata and Harper's work on two-dimensional type theory, which I will not get into, but this is just a reference for those of you interested. Right. I hope there are no questions so far, in the sense that this is just me trying to convince you that category theory sort of matters not only for mathematicians, but also to programmers or software engineers, to, well, at least in some specific domains.
Just for clarification, could you please repeat once again what are generics in Glasgow Haskell compiler?
So generics in Glasgow Haskell compiler are just, so this is a way for a user-defined type to have a sort of standardized generic representation that can be, which is basically a special representation of the type that allows you to write generic code.
Basically, it is sufficient. It is sufficient right now for me. So it is a tool to describe user-defined types, correct?
In a generic way, so that you can do metaprogramming, but in a safe way, not like in Lisp. No offense to any Lispers here.
I don't know.
Absolutely. So now we can get to that. Now that you know that category theory is really important and everyone should know it. Now, when you reasoning directly in category theory and homotopy theory can be hard, and this is especially true for higher category theory and higher, for higher category theory. And this is because once you have, once you not just have objects and arrows, but you have arrows between arrows and arrows between arrows between arrows, there are some sort of coherences that you have to check. And coherences are just checks that you have to, that ensure that everything just makes sense. These are just like simple, this would be a very bad analogy, but in a programming language, for example, if a variable is used but it's not defined anywhere, the program just doesn't make sense. So this is a very simple check that you might want to do. And in category theory, you have certain semantic checks, which are probably not super interesting on their own, but you have to check them to make sure that the structure that you have will behave in a good way. And in higher category theory, these coherences can spread to many levels, including infinitely many levels. And of course, to check all of those coherences on these many levels requires some ingenuity. And as far, again, I'm not an expert in analytical category theory, but as far as I understand, this is really hard to do. So, but people, of course, still do this, but this is one of the problems. And then synthetic theories basically try to internalize some of the common arguments that happen when you reason about category theory analytically, about analytic theory. And so you internalize some of the arguments, so you make them basically built-ins. Instead of proving them every time, you say, this is what is allowed, this is what we're allowed to use. And this is like a built-in in the sense that you do not look inside. Like again, with the programming languages, like you have a system call, it just works, and you don't care about its implementation. And of course, it can be interpreted in different analytic theories in different ways. So you can have different models. But now that you have a synthetic theory, it allows you to prove some things easier. And then proof assistance, right, and I have some examples here, but I can explain them in a moment. And then proof assistance basically use synthetic theories to check or even derive proofs in them, right? So for example, we have homotopy theory, which is an analytic theory. And then we have homotopy type theory, which is a synthetic homotopy theory, basically. And then for homotopy type theory, we have a lot of different proof assistants or libraries in proof assistants that are not necessarily homotopical in nature. For example, Unimath is a library for Coq. Coq is built on top of calculus of constructions, which is a different theory from homotopy theory, but you can model homotopy type theory to a certain extent inside of that, and then you can prove statements about homotopy type theory in this way. Cubical Ogda is an extension to Ogda theorem prover proof assistant, which adds cubical types. So there's this is one. This corresponds to cubical type theory, which is a version of homotopy type theory, and there are multiple experimental proof assistants. There's red TT, cool TT. There is cubical TT. TT stands, of course, for type theory.
Sorry. Okay.
Right, and so this is all for the there's also Arend. Maybe you have heard of that one. This is a proof assistant developed at JetBrains for homotopy type theory. This is and maybe interestingly, most of these proof assistants that are mentioned here, that are mentioned on the slide, they're implemented in either Haskell or OCaml. But Arend proof assistant is implemented in Java, which is I think is interesting at the very least. So anyway, and then on the category theory side, we have higher category theory. There are different higher category theories, but in particular, and there are actually currently there are several different approximations for a synthetic infinity category theory. Here I am talking about one specific such theory that was introduced in 2017 by Rio and Schulman. But there have been other approximations. So for example, two-dimensional type theory by Licata and Weaver. And recently there's been some development by Szynski and his team, and I think there are some other developments as well, which I do not cannot recall from memory. And so RZK is basically, at least for now, this is the only proof assistant that's based on this specific synthetic infinity category theory. So what I'm doing is I'm developing this proof assistant to be so that people who work in infinity categories can work in synthetic infinity categories and then check their proofs with the proof assistant that I develop. Does it make sense?
Okay, I would like you to call these people by names.
Oh, these people. Well, these people again.
You said for people who work in the infinity categories. Well, who are these people?
There are, I don't know all the people, but I know at least two people who are actively working with me on this. So which are Emily Rio and Jonathan Weinberger. Yeah, but there are other people who work in infinity category. For synthetic, yeah. Anyway, so this is the context. If there are no questions, then we move to the actual language and talk a little bit about what is possible right now. So again, this is going to be still an overview. I'm not going to give all of the definitions for the synthetic infinity categories. We can maybe get a deep dive into that another time. But today I thought it would be useful to just give a general sense of what proof assistant is about and what are some of the interesting features of the proof assistant and the theory and what we have achieved. So simply put, type theory for synthetic infinity categories, Rio and Schulman's, is actually what they present in the paper is not a type theory for synthetic infinity categories. And just that, they present what's called a type theory with shapes, which is a slightly more general theory within which some of the types behave like infinity categories. So usually, when you talk about types in a programming language, a common intuition is that a type is basically a set of values. Now, a set is a somewhat boring structure in the sense that you just have a collection of things, but you don't know how they are related to each other. So in that sense, a category would give you more information or more insight about the relationships between the points or elements in your type. And so the idea of this synthetic infinity categories type theory is that a type is supposed to represent not a set of possible values, but a category of possible values. Okay, so if someone is familiar with homotopy type theory, in homotopy type theory, a type corresponds to an infinity groupoid, which is basically a category where all arrows are invertible. So yeah. So to this end, what they do is they start with an intentional Martin-Löf type theory, which is a dependent type theory with dependent functions, dependent sums, and the identity type, and we'll get some examples of those in a second. But on top of that dependent type theory, which is sort of somewhat known, there are two important features. One is extension types, which basically allow us to say, and we'll see examples of this, which give us restrictions in terms of judgmental equalities on some parts of, let's say, diagrams. We'll see examples of that. And then we have also this taupe logic. So we have basically a Martin-Löf type theory, which is indexed by points in some abstract space, which basically gets us to diagrams, categorical commutative diagrams, for example, where vertices and edges and maybe some faces and tetrahedra, they're basically labeled with some types or terms in this Martin-Löf type theory. I will get to an illustration for this. Just sort of the important thing is that we take a somewhat well-known theory and we extend it with extension types and taupe logic, which are the important components here. And RZK is an experimental proof assistant that is based on this type theory. Right now, the working part specifically targets the infinity categories or the Simplicial type theory, but a fairly simple extension would be to support this entire general theory. In any way, the language is quite straightforward, and I will give you some examples of the syntax. And generally, it's inspired by the three popular proof assistants, Ogde, Koch, and Lean, which are all based on dependent type theory, which is important because that's also what this type theory is based on. So Right. So the type theory, like I said, basically consists of 3 layers. The first 2 layers constitute what's collectively constitute a topologic, and the last layer is the types and terms layer. So terms, you can think of terms as programs or expressions corresponding to a particular type. So, for example, here in the picture, you can see that we might have, for example, we might start off with a cube space. And in this particular case, we're actually talking about a directed cube. So we actually care about a direction for each dimension. And whenever we travel in that space, we can only travel in one direction for each dimension. And then in this space, we can carve out a shape. So, for example, we could carve out this. This is what's called a horn. I think this is notated like this, like lambda with 2 indices, 3 and 2. Doesn't matter what this means, but
is this cube hollow or solid?
The first one is solid because we are taking the entire space, and then inside of this space we select something. And in this particular case, we select basically 3 faces of a tetrahedron without the interior. So the interior usually could only be included if all of the if the boundary is already included. So here we cannot include interior anyway. And then what we do then is we take this shape and we label it in this Martin-Löf type theory. So this means that we give to each point we assign some value, and what's important is that this entire picture happens inside of a given type A usually. It can be more complicated, but for now let's simplify things. This entire shape determines a sort of a categorical diagram, and remember that types are categories. So this entire diagram happens inside of a single type, and it basically tells us how terms inside of that type are related to each other. So vertices become. Let me just enlarge this a little bit. Vertices become terms in this type A. So these are A, B, C, and D. And then edges in our original triangle correspond to arrows. For example, you can treat them as functions. So maybe you have here a type of types, and then A and B are 2 types, and then F is a function from A to B. Or you can have some other examples. And then the faces of the triangle, for example, this face corresponds to this face, but this face we don't. Well, here we do not annotate it like immediately in the picture. Instead, what we do is we say that M composed with G is equal to L. And so this equality, this corresponds to the fact that we have a face for this triangle. Right. So this is the basically tells us that the diagonal is the composition of the 2 other arrows. So, and again here.
It assumes that all objects are different.
No. The objects can be the same.
It could be, for example, just single object A and all these 3 basic matrices.
Yeah, identities. Yes, for example. Yeah. So I hope it makes sense. So this is the general idea. So they actually there are of course a lot of symbols involved, but logically speaking, we take Martin-Löf type theory and we add a language that describes abstract diagrams, and then we index. When we're indexed in those spaces, we get our categorical diagrams. And of course, since we can talk not only about points, arrows, triangles, we can also talk about tetrahedra, 4-dimensional tetrahedra, or it's going to be not tetrahedra, it's going to be something else. Oh, well, polyhedra. So anyway, we can talk about higher dimensional figures, and this basically gives rise to this idea of infinity, infinity stuff. I hope it makes sense. Any questions on this slide?
Questions from online audience, please. Either nothing is clear or everything is too clear.
Yes.
Two options.
Yeah. Okay, I will move on.
And no intermediate points.
Right. So just to give you a couple of examples of actual code, we'll only consider again this directed interval space, which is in the code it's written 2. In math notation, it's written this 2 with whatever like mathematically bold 2. And then we also can have directed square, which is just
Directed interval.
Yep. So a directed
interval.
Yes. So a directed interval 2 consists of a point, a designated point that is called 0, a designated point that is called 1, and actually we don't know what else is in this space, but we know that if there is anything, all of this has to lie on a line from 0 to 1, and moreover we have basically a way to compare 2 points in this space. So we don't actually know how many points are between 0 and 1. There can be 0, there can be infinitely many, there can be countably many, uncountably many. All those options are basically models, and this can vary very significantly. So in this sense, this directed interval space is abstract. So we can call 2 specific points, the endpoints, and we know that all other points are in the middle, and this is guaranteed by the axioms that we have for this. But that's all that we know. And then, of course, the 2-dimensional square would start with 0, 0. For example, you can have 0, 1, 1, 1. You can have 1, 0, and you can go here, here, here. And interestingly, you can go in this direction because you can increase both components, but you cannot go here or here. That is not allowed, because then you would have to increase along one dimension and decrease along another dimension, which is not allowed. Both dimensions are directed, and you can only move in one way. So this is a useful feature, because now this says that whenever you have a 2-dimensional space, it can actually always be split into triangles in a unique way. Great. So then in the code, we have the ability to then, of course, we have the internals of this, and we have the internals of this, right? Interestingly, so what we can do then is we can select subshapes from those spaces. For example, top would mean that we select all points in a given space. So in 2-dimensional space, we select everything. Bottom would correspond to selecting nothing, or logically this corresponds to false. Then we have this symbol that is reminiscent of logical end, which is the intersection of shapes. This is the union of shapes, and this in mathematical notation, this is denoted like this in the paper, but we're going to skip that. And the idea is that whenever you're given 2 points, you might not know what they are, but you can check restrict the kind of space that you're interested in to the part where they're equal. For example,
so this time it is not equality that is a statement about the 2 objects are equal.
Yes.
It is constructed.
Yes, exactly. So, for example, if we take a 2-dimensional space, and
I still need to clarify.
Exactly. If we have a 2-dimensional space, so we know that T and S are the 2 coordinates of a 2-dimensional space, right? Then we can say that, well, we want only to consider T's equal to S, and then that would mean that we only consider this diagonal, this red diagonal in the cube. And of course, we also have inequality that is specific. So all of the previous ones are available for all spaces, but this one is only available specifically for the directed interval. So of course, we will not have examples of other spaces in this talk, but I have to mention that. And then t is less than or equal than s would just mean that, well, in the picture that I drew, well, actually, let me fix the picture to match the way that it's usually done. So the second component goes down, and the first component goes horizontally. So then t is less than or equal than s would be this triangle here. I hope that makes sense. So this triangle is this condition.
By the way, Nikolai, I would like to recall that we should have some break, definitely, because
absolutely. Absolutely.
Please, select your role when it will be more convenient for you to have a break.
Logical, yeah, I think we need one or.
Okay, please go ahead.
Yes.
5 or 10 minutes is okay.
So here's some basic shapes that are involved in the theory and how you specify them in the proof assistance. So again, I'm not giving any mathematical notation here, since again, I expect most of you to not be familiar with it anyway. So we will just deal with the notation used in the proof assistant. So here we define a delta 1. So this is the name that we give to our definition. And the delta is of course used because these are going to be triangles just in different dimensions. One-dimensional triangle is of course a segment. Two-dimensional triangle is a regular triangle, and three-dimensional triangle is a tetrahedron.
By the way, how do you type subscript 1?
Subscript. This is superscript.
Superscript. Sorry.
Right. So there are extensions to the editors. For example, there's Agda mode, which allows you to do this, and there are things, some other extensions that allow you to do that as well. So there's Unicode input basically. Okay. Some extensions in editors that allow you to do that. So delta 1 is, and then here this is a syntax that means that it will be followed, this definition is followed by the type of this definition. The type of this definition is tells us that for every point in in an interval 2, someone asks a question. 1, 2, 3, 4, 5, 6, 7.
I hear you, but sometimes you are. Okay, I think the problem is on my side.
All right. Okay. So so we see that delta 1 is basically a sort of function that takes a point in the directed interval and returns a taupe. So what this means is that we get, and then in the body, so here this designates that after this symbol we'll have the actual definition, the term. Now this backslash t is not a tabulation. This backslash is like in many languages. This is just lambda without one of its legs. And
thank you very much. New knowledge. I did not know it before.
Yes, exactly. So like in many languages, this is that, and it's just that backslash is very easy to type. Of course, you could, I think, in the current version, you could also type lambda, but backslash is just what we do for now. And then what we say is we will take everything. So top here says that regardless of what point in the space we look at, we just say that it suffices, it works for us. So yeah, and this corresponds to this picture here on the right, which is a little bit small. Apologies for that, but basically the entire one-dimensional directed interval space. And then for 2 simplex, we say, okay, now we map not from a single to, but we map from 2 times 2. And here you can think of 2 times 2 as just a product of spaces. So it's a 2-dimensional space. But we say that we will only select points that satisfy that S is less than or equal than 2. That picture that corresponds to this picture here, where we select the top triangle.
If we selected everything, we would have the 4th point and we would have the arrows.
Yes, we would have also this and this and this. Yes, exactly. So, and with the 3 simplex, so 3 simplex is a tetrahedron, and we just so the convention is you introduce variables from left to right, and then you allocate them from in the reverse direction with the less than or equal to get the default sort of polyhedra in whatever dimensions you need. But usually 3 dimensions is enough, so I will not need much more. So this is how you select a tetrahedron, and here's a corresponding picture. So just to be clear, this dimension corresponds to T1, this dimension corresponds to T2, and this dimension corresponds to T3. So here we have 0, 0, 0, and here we have 1, 1, 1. So it should make sense. Right. So these are the basic shapes, and I think before the break, the last slide, if there are no questions for this one.
No.
I have a question. Why do you use the brackets after the lambda if the order is default?
Right. That's just because I do not yet support syntax for arbitrary tuples. Yeah, that's just not the feature that seemed high priority, so I didn't implement it. No other reason. So, binary parentheses. Yeah. So here, these parentheses are automatically inserted because this is an infix operator. It has to insert parentheses in some way, but comma is not an operator. It's a bit different. So for the actual tuple system. Yeah, but it's minor syntactic thing. Thank you for asking.
So there is always a tuple, not the correct version, yeah?
Yes, yes. What Antonina asks is that 2 times 2 times 2 is by definition the same as 2 times 2 times 2, because it could have been that these are 2 different types.
Yes. So move it to the left.
Yeah. Yes. Right now, this is automatically this. Yes. So.
One question.
So the 2 other important shapes are, of course, the boundaries of the simplex. So the boundary of one simplex is just the endpoints 0 and 1 without the arrow in between. And the boundary of a 2-dimensional simplex is, of course, the triangle without the interior. And you can hopefully see from the definition how we define it. So for 1 dimensions, we just explicitly say it's either 0 or 1. For 2-dimensional case, it's a bit more interesting. We say either S is equal to 0, and remember S is this one. So S is 0 means that we get this line here, and then this is sort of the first one. The second one is T is equal to 1, so this is T, so this is going to be the second one. And then S is equal to T is useful because we now can talk about this diagonal arrow. This is the third arrow, right? Good. Now these are, of course, shapes, but what we're interested in we're interested in labeling them. But before we do that, I suggest that we go on a short break.
Short break. Exactly. Thank you very much. 5 minutes break. I put this call on hold. In 5 minutes, I will be back. But you can use the same Skype session to chat, to discuss you should not unmute yourself or mute yourself. Just to compose myself. И так как это, в общем, слушаю уже 4-й раз, я привык. There are two levels of different levels of understanding. Some people understand indeed, some people just have habit too. I am from the second kind. But nevertheless, at least I have habit too.
Николай, в перерыве спрошу офф-топ. Вот там понятно, что вы рассматривали proof ассистенты. Что вы скажете про систему компьютерной алгебры над категориями в Джулии? Просто я видела, что она есть, я не смотрела, что там вообще происходит и насколько она прикладная, но стало интересно. Значит, там что-то приводится к нормальной форме над категориями, что-то там нормализуется и какие-то эквивалентности используются.
К сожалению, ничего не могу сказать. Я знаю то, что она есть, вот, и больше я ничего не знаю. К сожалению, с Джулией я не знаком. Вот, я знаю то, что есть проекты, которые используют тоже теорию категорий там, в частности, для того, чтобы переводить из разных представлений между друг другом и получать какие-то интересные результаты. Какой-то интересный доклад я слушал год назад, по-моему, но я забыл. Вот. Но, к сожалению, сам лично я не имею никакого опыта и никакой компетенции говорить что-либо про эту библиотеку.
Спасибо, просто было интересно, потому что она большая, вроде как много прикладных областей в ней затронуто, теория категорий там для геометрии, для чего-то еще, и подумала, что может быть какая-то определенная связь есть.
Наверняка есть. Мне надо посмотреть. Спасибо, что напомнили об ее существовании. Да, надо обязательно посмотреть, что в ней есть. Я в основном смотрел на действительно proof ассистенты, которые, во-первых, основаны на системах типов с зависимыми типами. Вот. Есть еще и другие теорем-проверы и proof-ассистенты, которые на других теориях основаны, в том числе на теории множеств, например. И там тоже есть формализация теории категорий. Вот. Библиотеки, с которыми я работаю, формализации, с которыми я работаю, они в основном формализации математики для математиков. Да, я не знаю, we can switch to English, maybe.
Нет, все равно все остальные, все слушают. Запись сейчас будет возможно.
Okay. Yeah. So I don't know all libraries on category theory. I know some libraries in Haskell. I know some formalizations in Clock and Unimath. I know some. And I know some. I mean, the only ones that I know very intimately are probably Haskell, Clock, and the proof assistant that I've implemented. I also know a little bit about others, about Agda in particular, a little bit about Lean, but I don't know much about Julia or some of the others, other proof assistants that are not based on dependent types.
I have no naive question, but for me it is much more valuable from pedagogical point of view or educational point of view. Well, what do you think while we have a break? Should everyone, or let me say every second, know what is in our university, what is Martin-Löf type theory and what is system F? What do you think? I believe that at most 10% is aware here about what these theories are. What do you think? Should we teach this topic?
Right. So the question is, should we teach Martin-Löf type theory and system F at the university? I don't know. I personally, I'm biased, of course. This is like. For me, this is a good way to have I think this is the kind of mathematics that helps structure thinking for engineers, for software engineers.
For
But
engineers, not for scientists.
yeah, I think so. Yes. But
What do you think?
At which level?
Here in the class we have 3 people. What is your opinion?
At which level you're talking about? Bachelor, master, or PhD?
Let me say bachelor.
Bachelor?
bachelor, yes.
I don't even know what this theory is really, but I don't think it's suitable for bachelors. I mean, programming paradigms is already too difficult for many people.
But that's okay. If we talk about programming paradigms, the most difficult part is to forget the programming that you already have learned. If you have learned one programming language or one paradigm, it's very hard to unlearn or forget it, like suspend your learned stuff for a moment to switch to another.
It is very difficult to think different.
Yeah, it's very difficult to think differently. So if you were to introduce like type theory, for example, to bachelor students, it's perfectly fine to introduce that in the first year when they are fresh. When they're fresh, and I mean, personally, again, I'm biased. I think that going like from Haskell, for example, going to C++ is easier than going from C++ to Haskell. So in that sense, if you think that teaching Haskell at all is good for whatever reason for the students, then probably it makes more sense to teach Haskell first and then to teach C++. But if you don't think that Haskell is worth learning for most of the students, then you don't teach Haskell to most of the students and you just teach C++ or whatever. So it's same here. If you think that studying type theory would help people in the future, then of course, yes, they should study type theory. But
so basically, no answer. If you think that it will be helpful.
No, it's a bit different. No, it's a bit different because it's not just if you think it's useful, teach it. It's I think that if it's useful, then it's better to teach it early because a lot of other things make a bit more sense through the lens of either functional programming or type theory. And this is particularly.
We should continue.
Just finishing that this is particularly, I think, valuable for people involved with computers because type theory, the whole idea, at least the modern idea, is that it's computer-friendly mathematics. So it's, or at least the kind of mathematical reasoning that is, at least for the most part, computer friendly. So you can teach a computer to reason this way. And this is very different from a lot of other mathematics that is, Anyway.
So let's continue presentation. Let's continue Nikolai's talk.
Yeah, yeah. Right. So now, before we label our diagrams, we need to understand what we can label them with. And again, I will just give a few simple examples. I'm gonna skip some parts probably. If it becomes not understandable, then we'll just get to the next section, I guess. So just if anything is not understandable, let me know. So we'll start with dependent functions. And dependent function types, the idea is very easy. It's a function, but the type of the result may depend on the value of the argument. So here we have three different definitions of an identity type, and the purpose is first to show the dependent functions, but also to show you different syntax so that you're not scared of it used later. So in the first definition, what we see is the identity here is a function of two arguments, and here we're using this, we're separating arguments with arrows, and as usual, this is interpreted like this. So this is a usual carried function type. But we say that the first argument is whatever this thing is, and this U stands for the universe, and specifically we mean by this like the universe of types. So this basically just says type, but it's shorter to write. And we write it U because I did this basically by because I had a habit of writing types with one symbol.
The top type.
No, this is not the top type. This is the type of types.
So A is a type.
So we now know that A is a type, and we can now use A to define the type of the results, which is a function from A to A. Now here we can also specify the name for the argument of type A, but we can also just write a function from A to A. Now in the body, we again have this lambda A x. So we introduce two arguments, A and X, and we produce X on the right. Now you can notice that here and here we introduce the same thing twice. One time to use in the types and one time to use in the body. Well, here we don't actually even use it in the body. We could have just said that we ignore this. So a simple convenience that will be probably seen later is that we before we use this column, we introduce all the parameters that simultaneously are introducing the type parameter, and immediately is available in the definition of the term.
Do they have to have the same names? A and X in the signature and in the definition?
No, they don't have to.
I have a stupid question.
Yeah.
As you type U.
Type U, yes.
As U is U of type U.
Oh yes. That is not a stupid question. That is very very good question, because indeed the type of types is itself a type of the same type. Now this is what's called a type and type, which is actually something that is that can lead to inconsistencies in the logic. However, it is somewhat hard to bump into. It's not super hard, but it's sufficiently hard to bump into inconsistencies because of this. So a lot of proof assistants, at least on that are experimental, use this. And this is actually used, for example, in Unimat library in Coq. They use type and type, even though technically you should have like a hierarchy of universes. You should have U1, which has type U2, which has type U3, etc.
Okay, like in Coq, right? In Coq, you have this hierarchy of types, of universes of type.
Yes.
Yes. Is there any reason to not? Is it difficult to have this hierarchy? Is there a reason to accept this inconsistency?
Right. It's difficult to implement this for all the cases, because usually when you write here identity, for example, you don't want to specify that it's valid for U1, because then you would need at some point an identity for the universe 2, right? Mm-hmm. So instead, what you do is you say this is valid for all universes UK, where K is some index, right? So you would need something called universe polymorphism, right? But then the problem is when you have multiple types, like you have A of type UK and you have B, for example, of type UL, then you have to understand how these indices relate. And sometimes this can be easy. You can say that K is equal to L plus 1. Sometimes you can say that K is less than or equal than L plus 2. Or you can have something else like some other weird stuff that you would have to deal with. And because in general it's more complicated to deal with this kind of polymorphism, in experimental proof assistance it's excused, I guess, to assume type and type, at least for the first stages of the formalization. But yes, technically this leads to inconsistencies like immediately.
Okay, thank you.
Thank you for the question. This is very, very important. Right. So now here's a bit more involved example. Now this is a very simple function and some proof about this function. So flip is a function that takes a function as an argument, and I will just highlight the actual important argument here. This is a function, and essentially it's a function that takes an argument of A, an argument of B, and returns an argument of C. The only thing, though, is that C is not just a type. This is what's called a type family. So it's a type that would be determined by the values of the first two arguments. So this is a function that takes two arguments of two potentially different types. They could be the same, but in general they're not, and return some result that may depend on those values, the type of which may depend on those values. And what it says then is that we can take this function and we can produce a function that takes the arguments in a different order, y first and x next. And you can see that even though semantically this is a very simple function, because you just take x and y and you produce yx, and you can see the definition is very simple, right? It's just lambda that takes yx and produces f of xy, right? Even though the implementation is very simple, the type now becomes more involved. Now, this is just the dependent types. This is before we add extra layers with the topes stuff, etc., etc. So even on this small example, you can already see that types become, or the specifications of this program is already more than, occupies more space than the program itself. And then flip ID, flip is ID is a proof that if we take a function f and then we apply flip twice to it, then we get back the same function f as before. And again, the proof here, the actual proof, is the proof by reflexivity. The way this works is, what it does is it sees the right-hand side. So reflexivity, of course, only works if both sides of the equality that we're trying to prove is the same thing. Now, of course, I didn't talk much about this, but equality of terms is also a type. So whenever you have x and y elements of type A, there is a type called the identity type or the path type from x to y in the type A that says, and elements of this type are witnesses that x and y are equal, in whatever sense that means.
But there is no general identity. Each identity is bound to some particular type, is it?
Yes, exactly. So when we write here equals without the subscript, it's actually because the type, the proof assistant can figure out that the type we're talking about here is actually this huge type. It's the identity in this type. But you can figure this out automatically. It's at least somewhat smart in this sense. And when we say REFL, what it says, so REFL is the only inhabitant that exists for all types. For some types, there can be more, but REFL is the only one that exists for all types. And the type of it is, of course, that x is equal to x for any type A and for any element x in that type. So we can only use REFL if the proof assistant can figure out that actually on both sides we have the same thing. But in this case, it's fairly straightforward. All that you have to do is you have to look at the right-hand side here, and you have to evaluate it. Well, you have the definition of flip, right? So it's this thing, right? So technically, you have to first do what's called an eta expansion before you can apply flip properly, right? Or rather, you get, let's see, the first flip of f will basically produce lambda y x f of xy, right? And then the second flip is applied to this thing. So we take all of this and we apply flip to this. And of course, what we get is lambda y, I don't know, prime x prime. And then this huge thing in parentheses applied to x prime y prime. And then after we expand everything under this lambda, we will see that actually what we'll have in the end, again, this will reduce to lambda y prime x prime f of y prime x prime. But this is the same as just f by the eta rule. So the proof assistant can compute all of this. These are not very complicated rules. So it can do all of that and understand that indeed on the left and on the right we have f. So reflexivity is fine to use here, right?
I have another question.
Yes.
May I ask? Here you wrote refer as type x equal to x with parameter a. I guess that if I change x or a, it is not the same refer, right?
Right. So technically, yes.
So here you are using some implicit arguments, and your proof assistant is able to infer these implicit arguments.
Yes. Yes. So technically, implicit arguments in general are not supported in the proof assistant at this point. But for the built-ins like REFL, yes, and the equality sign, yes, these implicit arguments are supported because that helps tremendously. Yes. So you could write also in the proof assistant, you could also write explicitly REFL underscore, and then in the whatever you could write f and then this huge type that we have. So you could write that explicitly, or you could just write f and then because we know the type of f, that would also be enough. So there's syntax to give partial to give some of this information if needed, but most of the time it's already in the context, so REFL is sufficient. All right.
Okay, nice.
Thank you. So I think we're gonna skip this one. There's a transport. I don't think that's very important. I will rather go to the interesting types that we have. So here is a definition of the type of all arrows in the type A from X to Y. So remember that the idea is that a type A basically is a category, which means that it has a lot of points which are like elements of that type. And then there are arrows between some of those points, right? And maybe to themselves also, right? And what we want to do now is we want to have a type, we want to fix 2 points in the type, and we want to ask, what is the type of all arrows between these 2 points? And the way that we do that is by saying, okay, we first take this shape, which you remember is a one-dimensional simplex. So it's 0, 1, and the arrow in between, right? And then what you do is you basically map 0, and here you and you map 0, 1, and all of the points in between, which again we don't know how many there are. We map them to somewhere in the type A, right? And specifically then in these square brackets, we can specify some constraints with definition, some specific constraints, where we say that if t is equal to 0, so specifically the point 0 has to be mapped exactly to x, and then the point 1 has to be mapped to y. But then of course the arrow itself has to be mapped to something here. It has to be in the type A, but we don't know what. And so because we have to provide that, so we have fixed the endpoints, but the rest has to be provided. So this is the extension type. This is basically a type that is where we're indexed in some shape, and then we have restrictions for parts of that shape, and all of that happens in some type. Now, again, this is a simplified picture in the sense that the type itself does not depend on the points in the abstract interval. It can. That would be a bit more complicated to draw, especially, so we're going to skip that. Does that make sense?
It looks like.
Okay.
I don't have questions right now.
Of course, it's at this point it shouldn't. It probably is not very clear why we would need this type specifically, but the intuition should say that, well, we want to talk about categories for some reason. So this is helpful for that. Now, another interesting type is hom2. Now here you can see that we start with the type A, 3 points in that type. So we have we have X, Y, and Z all in type A. And then we have this F, which is a hom in type A from X to Y, which means that essentially this represents some arrow from X to Y in type A, right? G is from Y to Z, and H is from X to Z. This is H. And then this type says that we take now all the points in the two-dimensional simplex, so in the triangle, such that if t is equal to 0, which corresponds to this entire thing, it has to be equal to f. Now, importantly, f is of this type hom, right? Which gives us labels for all points along this this upper edge of the triangle. It's not just the arrow between x and y; it includes x and y themselves. Right. So when we say that when t2 is equal to 0 and t2 goes here, t1 goes here. So when t2 is 0, that means the upper arrow together with the endpoints should be the same as f. But then if t1 is equal to 1, which would correspond to this, so this corresponds to this, this would be g. But now, interestingly, between this and this, we have an intersection, right? They intersect at the point y. And this is a burden of a proof assistant at this point to check that actually these two terms, f and g, match on the intersection of these two shapes. So the intersection of these two shapes is going to be t2 is equal to 0, t1 is equal to 1, which is a single point in the two-dimensional space. And now the proof assistant has to check, well, is it actually true? Because if it's not, this type at all doesn't make sense. Is it true that f at that point is equal to g at that point? So if we check f when t1 is equal to 1 is y, and g when t2 is equal to 0 is also y. We know that from the type of hom. Why do we know this from the type of hom? Well, this is because by definition, it's a type where we know exactly what happens at 0 and 1. So we can trace this, again, we can compute what happens for these two things. And this is one of those very simple, but still coherence checks that usually in an analytic theory, you have to manually check for, well, here is very simple, but for complicated terms, this might not be as simple. And here, again, the proof assistant has to check that these two things match. So this is a coherence check for the definition. And similarly, we have two more intersections here and here for x and for y and for z. We have to check that those are the same. And so probably at this point you can see that one of the difficulties of implementing the proof assistant in general should be that, well, in general, you instead of variables like y and x and z, you might have arbitrary terms, arbitrary open terms, so that you cannot just compute to a specific value. So in general, what you have to do is you have to compare two terms and check whether they are the same term. Now, it turns out that for the formalizations that we're dealing with so far, the simple normalization algorithm that is not complete is sufficient. But in general, this this is one of those things that prompted me to think and learn about equational unification. This is not yet incorporated in the current proof assistant, but this is one of the things that I've been working on, and I plan to integrate into the proof assistant in the future. So the idea is that if the simple algorithm doesn't work, then perform full equational unification that maybe will check and allow some of the constructions that otherwise wouldn't be allowed. Right.
So right now, simple normalization is implemented, is it?
Yes, right now simple normalization is implemented. Well, with eta conversions and it seems to be fine for all of the formalizations that we have so far. It seems to be working wonderful. Right. I think we can skip this one. Again, I'm looking at the time. I guess we have, how much time do we have?
Well, I believe we should either stop in 10 minutes and then we have discussion, or maybe continue for volunteers somewhere later.
Okay.
So your preference.
Right. So
either 10 minutes and then discussion.
I think 10 minutes and then discussion is good. Yes. So there are some more complicated, but still these are like basic things that you need to do something more interesting. I will skip this for now, and we can have a more.
In this case, you can stop in 5 minutes.
No. No. I want to talk instead about a few interesting things. So first of all, one thing that I'm trying to do in the proof assistant is I'm trying not just to build a basic proof assistant that is write only, in the sense that you write your formalization, it checks out, and you say, okay, I will just leave it there. I would like to have formalizations like a part of the explanations or the reasoning. There should be some text that corresponds to the formalizations that are being made. Maybe sometimes formalizations can be sort of hidden partially or something like that, but it shouldn't be that you have like 1,000 lines of formalizations without any explanations, or just if you just have code comments, that's usually not enough. So from the very beginning, what I'm trying to do is I'm trying to support and promote a little bit literate programming, in the sense that you write immediately something that is supposed to be a text with code blocks that corresponds to formalizations. Now we are not following that very closely, but I can show you some examples in the on the website of the proof assistant. So for example, when I'm talking about sections and variables, there is some text and some examples of the code. Yeah, the skipped slides can definitely account for another talk. But the idea is that you have text that explains something.
Wait. Regarding continuation of your talk, Antonina asks, maybe it deserves, skip slide deserves additional 40 minutes talk?
Sure. I mean, we can have another 40 minutes talk or 1.5 hours.
My suggestion right now is let Nikolai proceed as he plans, and if there will the question during discussion and wish to continue, we can schedule another meeting.
Yes, exactly.
For volunteers.
Exactly.
So, thank you, Antonina, for questioning. Please continue.
So again, the idea is that when you these formalizations do not exist in a vacuum. You have an explanation text for reasoning why these formalizations is interesting. What are the problems? Well, so all of that should go by default with the formalization. So to that end, all of the formalizations that we're doing, we try to do them in Markdown with code blocks that isolate. And right now, not everything is properly documented, but we hope to fix that. And another bonus is that all of the formalizations are like available for browse, for at least browsing in some capacity by interested people. So it's much more discoverable and understandable, I think, than just pure source code. Another thing is automatic visualization. And again, I will just, I will show that on the website. I have a documentation for that. So all of the pictures that most of the pictures that you saw in the presentation were actually automatically generated from the code. So it's not that I've written a diagram for each formalization. It's actually the renderer is sometimes powerful enough to render some interesting non-trivial diagrams. It's still not as useful as it could be. It's very early stages and experimental. But here, for example, there's a formalization that technically first takes a prism construction, and then from that prism extracts an internal face. And the automatic renderer can just look at the code for this and render a corresponding diagram with some proper labels. So some labels are skipped if they are not simple enough, but those that are drawn automatically. Yeah, so I think this is a nice feature again that should help visualize and understand proofs that are done in the proof assistant. Right, explicit assumptions I will just skip. That's an interesting feature on its own, but I will not talk about this much. And so the final thing that I would like to end this presentation with is some of the applications for the proof assistant that has been developed in the spring. So first, I would like to briefly mention why should we formalize mathematics at all? For some reason, I particularly like the story of that Vladimir Voevodsky has been talking about, his personal story, that he has had some proof, and then 12 years later, someone claimed that the theorem was actually not valid, and then 10 more years have passed since that counterexample, that the authors of the paper actually agreed that yes, indeed, there was a mistake, and not just the proof was wrong, but the theorem was false. Mm-hmm. It had to be weakened, I believe. And after this, the story that scared Voevodsky a lot, he became thinking about computer assistance for formalizing mathematics, and that's where this journey with, especially with homotopy theory, has fully started, I think, and Unimath library especially. So yeah, he asked if there's a complex equation. If it were a complex linear equation, we could have checked it on the computer, but why cannot we check proofs of a theorem? And so to this end, we're formalizing mathematics, and in particular, the original paper that introduces the type theory for infinity categories, it does a lot of proofs in that theory. And one of the milestones is proving the Yoneda lemma, which is a very famous, of course, lemma, and this is a version for for covariant type families. There are several versions of this unit lemma, even in infinity category theory. So this is the covariant version, and yeah. So we have started this collaboration in March. Emily and Jonathan, they contacted me, and I've been very happy to work with them since then. And the goal of the project, of this project, is to formalize the unit lemma for synthetic infinity categories. And it is formalized, and it's proved, and it's like the proof works right now. That's not quite the end. There are still some things that we want to still formalize around the unit lemma. And another part of this project is to compare formalization of this result with, for infinity categories, with similar proofs of the unit lemma for regular simple one categories in other proofs that is already done in other proof assistants. And Sina Hazratpour has also contributed some formalizations in Lean to that end, but we haven't properly compared them yet. And of course, we want to compare with some other proof assistants as well. Now, interestingly, perhaps most excitingly for me as the creator of the proof assistant, it actually helps find a bug in the original paper that the proof assistant is based on. So there's a proposition about some proposition about covariant type families, and the proof, you can see, you don't have to care about the proposition very much, only to see that blah blah blah, it is covariant if and only if A is a single type. And then the proof actually here proceeds to go through a series of equivalences. So instead of proving this in one direction and then in the other direction, it proves it sort of in both directions simultaneously by just a composition of equivalences. Mm-hmm. The problem is one of the equivalences, specifically proposition 510 here, one of its assumptions is that A is a single type, which is something that we're trying to prove. And this was missed in the paper, and I guess by the reviewers of this paper. And it only became apparent when Emily was formalizing this proof. So yeah, luckily the proof could be fairly easily fixed. I like for myself, I had to think a little bit to understand how to fix it, but the fix was not very difficult, and I was able to formalize it and submit a pull request a fix. And Emily and Mike will be updating their paper on the archive soon. But this is an interesting result, I think, for me. Right. So what's next? Well, we're going to improve the language because it's very basic right now. There's lots of stuff that I want to implement. And in particular, one of the major things that I'm interested in is incorporating proper type inference based on equational unification that I've worked on recently. But there are other things that I want to implement. I want to work and improve RZK tools, and any help is, of course, welcome here. I'm looking for Abdurrahman here. Of course, we want to formalize more of the infinity categories. We want to complete formalizing everything in the original paper, but then there is also another work. There is a thesis by Jonathan Weinberger and their paper with Buchholz, which introduces synthetic fibered infinity categories. There's like more interesting stuff to formalize, and it's much more technical than what I have seen in Emily's paper. So it definitely would benefit from formalizations, I think, at least for me to understand everything. And then there are also like whatever we can work with right now is what's called simplicial type theory, because we base everything around triangles. But there are other basic shapes that we can base a higher category theory on. We can base them on cubes, we can base them on globes, and those give different geometries and different interesting things. So this is for the future. So sorry, I don't have a thank you slide let me just thank you with my words. Thank you everyone for listening to this talk. Now, if you have any questions, I will be happy to answer.
Questions, please. While people are thinking about questions, may I ask some naive questions? Indeed, I have some naive questions. Firstly, why this acronym RZK?
Right. So, well.
Next will be also naive, but a little bit more.
So, in the real and Schulman type theory, there are two kinds of types. There are sigil types, which basically correspond to pre-categories, and there are RESC types that correspond to categories. So RESC and sigil are the names of two mathematicians that worked on infinity categories, in particular on high category theory. Right. So RESC is just the name of one of the mathematicians, and this name corresponds to the type that they use for the categories. So I thought it was appropriate to sort of use his name, but in a shortened form, because this is an experimental proof assistant. If it becomes a full working and great proof assistant, then maybe I will add the E letter so that it becomes a proper word.
So how do you read it? How do you read this acronym?
RESC.
RESC.
Yeah, REZK is the name of the.
I understand. That's how to read that acronym.
Yeah, you can read it as RZK or as RESC, but yeah, it's just RESC without one letter. It's not.
Next question is a little bit methodological. Why to develop from scratch a very new proof assistant? Why not to try to build a special library or something like this on top of existing general purpose proof assistant? For example,
Right. There are two or three reasons. One, well, it's fun. Two,
it was my hypothesis.
But of course that's not the only thing. Two, it's actually quite difficult to implement a plugin to another type theory. At least for me, it seems to be much more difficult because existing proof assistants like Agda or Cog, they are huge projects, and it's not trivial for me to just get into them and add this. Another thing is that the type it's not possible to just do a library in the sense that these extension types, they have to check that two things are equal by computing that they're equal. This is not very easy to model in a library. You really have to have this as a feature in the language. At least I believe so. Maybe for.
I trust you because I have no experience.
I mean, in general, it's true. Specifically for the formalizations that we did so far, maybe a library would be enough, but I didn't try that because, again, in general, this would not be true. But also, Agda has a lot of features. It's not just a Martin-Wolf type theory. It has a lot of stuff, and I don't know exactly how well all of the top layer stuff how well would it interact with all of the Agda functionality, for example, if I were to make a plugin for Agda. So there's too many unknowns, a high bar for entry in the sense that I have to be proficient with the Agda infrastructure already, right? So, but on top of all of that, if you have a huge project already that definitely has bugs, I mean, I don't say that my proof assistant doesn't have bugs. It probably has, but when you have an implementation that is like tens of thousands of lines of code or hundreds versus just 2,000 lines of code, it's much easier to verify the verifier, right? So it's a bit more trustworthy. Of course, this I'm writing on my own, and I have just 2-3 users, something like that at the moment, and Agda has many users. But again,
so community is a value.
Yes. So there is a trade-off. Yeah, I think there was some other point that I had, but I forgot it. I think these are enough reasons.
But basically, just for fun is sufficient. Indeed.
There's another interesting idea is that the way that compilers and proof assistants are implemented, I think the tooling and the libraries around the process itself of developing proof assistants and languages is not yet at its best shape. And in the sense that I think there is a certain amount of things that could improve just in the design space of proof assistants themselves, and in particular in the implementation, which I didn't talk about today. I use second-order abstract syntax, which I enjoy very much working with, which I think is very rarely used by anyone. And I think this is something that again contributes to the idea of how you can, in a more easy way, implement a new proof assistant. So if you have another type theory, I think my proof assistant sort of demonstrates indirectly a way to implement another proof assistant in a fairly short period of time that would be fairly trustworthy. I hope it makes sense.
Thank you very much for your answer. Questions from online audience, please. Antonina, Antonina left. So, any question from online audience? Daniel, Natalia, Dmitry.
I may suggest to implement rich proof automation. For example, automatic proof strategies.
Right.
So how much automatic is basically your proof assistant, or it is just assistant?
For now, it mostly checks stuff, but as Daniel has mentioned before, some of the built-ins already can figure out some of the implicit variables. And once I introduce unification into the type system, I can have proper implicit parameters and auto-bound parameters that are like some interesting features. On top of that, yes, you could have tactics or this proof search strategies implemented, like in many proof assistants. Maybe for some proofs, this would actually be useful. For now, though, we sort of try to be so even though on the one hand it's a downside of the proof assistant that everything has to be explicit, on the other side the users right now have reported that they actually like this feature at this point in the formalization because they see everything and they understand everything better this way. But of course some of the proofs become very large and there have to be some support to shorten them. Not yet in terms of tactics, but we try some other things.
Well, more questions, but please be aware. My accumulator is almost empty. Computer will die very soon. So just the last question. Unfortunately, I did not take charger with me. Any other question? If no questions, let's thank speaker. Thank you, Nikolai, indeed. There is demand in our Telegram chat to continue and present full details, but since we are very busy during the next week, it is question when we will be able to continue or provide details. Please think and answer Antonina in Telegram chat. Please. In principle, to make appointment for a couple of people, couple is not exactly two. Yes. Not exactly two. It is easier than to discuss right now. So thanks everyone for joining us. Thanks Nikolai once again. And bye. Goodbye. See you next time.